The Sun, our nearest star, is an incredible powerhouse that sustains life on Earth. This massive ball of plasma, primarily composed of hydrogen and helium, exhibits a complex internal structure and dynamic behavior. With a diameter of about 1.39 million kilometers and a mass approximately 333,000 times that of Earth, the Sun is an extraordinary object of scientific inquiry. To understand its structure, we can break it down into several key layers and regions, each playing a distinct role in its function. At the very heart of the Sun lies the core, a region where nuclear fusion takes place. Spanning roughly 20–25% of the Sun's radius, the core reaches temperatures of around 15 million Kelvin and pressures of over 250 billion atmospheres. Here, hydrogen nuclei fuse to form helium in a process known as the proton-proton chain reaction. This reaction releases an enormous amount of energy in the form of gamma rays and neutrinos. The energy generated in the core is responsible for the Sun's luminosity and the heat it radiates into space. Neutrinos, nearly massless particles, escape the core almost immediately, providing direct evidence of nuclear fusion. However, photons take thousands to millions of years to reach the Sun's surface due to the dense environment within the core. Surrounding the core is the radiative zone, extending from about 25% to 70% of the Sun's radius. In this layer, energy is transported outward by the process of radiative diffusion. Photons generated in the core scatter off particles in this dense plasma, gradually moving outward. The temperature in the radiative zone decreases from approximately 7 million Kelvin at its inner edge to about 2 million Kelvin at its outer boundary. This region is incredibly stable and lacks significant convection due to the steep temperature gradient. Beyond the radiative zone lies the convective zone, which extends from about 70% of the Sun's radius to its visible surface. In this layer, temperatures drop below 2 million Kelvin, allowing heavier elements to remain ionized and facilitating the formation of convection currents. Hot plasma rises to the surface, cools, and then sinks back down, creating a dynamic cycle. The convective zone is responsible for the Sun's granulated appearance, observed as granules on the surface. Each granule is a cell of convective motion, typically about 1,000 kilometers in diameter. This layer plays a crucial role in shaping the Sun's magnetic field through the process of dynamo action. The photosphere is the Sun's visible surface, a thin layer roughly 500 kilometers thick. With temperatures averaging about 5,500 Kelvin, it emits the light we see from Earth. The photosphere's surface appears granular due to the underlying convection currents. Sunspots, dark regions on the photosphere, are caused by localized concentrations of magnetic fields that inhibit convection, leading to cooler temperatures. These regions provide insights into the Sun's magnetic activity and its 11-year solar cycle. Above the photosphere lies the chromosphere, a layer approximately 2,000 kilometers thick. With temperatures ranging from 4,500 Kelvin near its base to 25,000 Kelvin at its top, the chromosphere appears as a reddish glow during solar eclipses. This layer is home to spicules, jet-like features of rising plasma, and is a site of significant solar activity, including flares and prominences. The chromosphere plays a key role in the transfer of energy from the Sun's interior to its outer layers. The transition region is a narrow, irregular layer that separates the chromosphere from the corona. Here, temperatures rise dramatically from about 25,000 Kelvin to over 1 million Kelvin. The mechanisms driving this rapid heating remain an active area of research, with theories suggesting the involvement of magnetic reconnection and wave heating. The corona is the Sun's outermost layer, extending millions of kilometers into space. With temperatures exceeding 1 million Kelvin, the corona is much hotter than the underlying photosphere, a phenomenon known as the coronal heating problem. The corona emits X-rays and is visible during total solar eclipses as a pearly white halo. The corona is also the source of the solar wind, a stream of charged particles that flows outward into the solar system. Coronal mass ejections, CMEs, Massive bursts of solar wind and magnetic fields can have significant effects on Earth's magnetosphere, causing geomagnetic storms. The sun's magnetic field is a fundamental driver of its activity. Generated by the movement of conductive plasma within the convective zone, the magnetic field undergoes an 11-year cycle of polarity reversal. This cycle is characterized by varying levels of solar activity, including the formation of sunspots, flares, and CMEs. Magnetic reconnection, where oppositely directed magnetic field lines break and reconnect, releases immense amounts of energy and drives phenomena such as solar flares. The sun's magnetic field also shapes the heliosphere, a bubble of charged particles that encompasses the solar system. The sun's dynamic behavior influences the entire solar system. Solar flares and CMEs can disrupt Earth's communication systems, power grids, and satellites. The solar wind interacts with Earth's magnetic field, creating auroras near the poles. Understanding the sun's activity is crucial for predicting space weather and mitigating its effects on modern technology. Advances in technology have enabled detailed observations of the sun. Ground-based observatories, space telescopes, and solar probes provide valuable data about its structure and behavior. Missions like the Parker Solar Probe and the Solar and Heliospheric Observatory, SOHO, have revolutionized our understanding of solar physics. The sun's structure is a marvel of nature, with each layer contributing to its function as a life-sustaining star. From the nuclear fusion in its core to the dynamic activity of its outer atmosphere, the sun continues to captivate scientists and laypeople alike. As we deepen our understanding of this stellar giant, we gain insights not only into the sun itself, but also into the broader workings of the universe.